Hello and welcome to Lesson 4 of CE 3372 Water Systems Design, and the topic of today's lesson is pumps and lift stations and certain features of pumping, in particular net positive suction head. This is a long lesson, so if you're watching it on video, um, bear with it, fast forward from the boring parts and go slow and take notes on the less boring or the parts that are new knowledge for you. So as an overview, we're going to describe pumps themselves as mechanical objects. This is mostly a show and tell, cool pictures, funny anecdotes. Suction requirements, and then system and pump curves. There's an example or two that's in the actual PowerPoint presentation that I'm using, but I'm also going to repeat the example using some of the online tools that are developed to illustrate how the system curves look and how a pump curve might be selected to match a particular system. In both the cases, I'll use fairly hypothetical setups, so bear in mind that I'll be making up numbers mostly to cherry pick the example, but the principles apply to actual pumps and actual systems. So first we'll start off with pumps. So what are pumps? Well, they're mechanical devices that transfers mechanical energy to move fluid, in our case a liquid, which is water, and it lifts water from lower elevations to higher elevations. The things that do this are called the generic name of lift stations or pump stations. They also can be used to increase pressure in a system. If it's a liquid, that'd probably be called a booster station. If it's a gas pipeline, there would be called compressor stations. So in the photograph here we see a pair of pumps in beautiful seafoam green, but we're actually talking about these kind of pumps that are now in the image. That's a pump and a motor. The part that's the pump is actually just that portion, and then this portion here is the motor that provides the energy to operate the pump. Inside this box here, this is the pump housing, and inside it is an impeller, or think of like a little propeller looking like thing. That hole right there is called the pump eye, and this is the discharge side. So Q out. This is incredibly harder than I thought it would be, and then this one is Q in. Q in. Pumps come in different sizes, configurations, and shapes like everything. So here's a large axial flow pump, and you can see from the size that this thing is big enough to eat entire human beings. So this particular pump, this is a hurricane barrier pump, so I am pretty much of the opinion that the water would come up this duct here, and the housing that's been removed from the pump directs the water so that it would flow this way, and obviously can't go through the impellers, but the impeller, let's see from the impeller shape, the impeller is rotating that way, and it pushes water along this axis, and this would be called an axial flow pump. So named because the flow direction of the water is more or less in the same direction as the axis of rotation of this large propeller thing, which is called the impeller. This particular pump wouldn't produce very much head, so not a lot of ability to lift water very high, maybe at best 10 or 12 meters, but it can do it at enormous flow rates, 50, 60, 70,000 gallons per minute, maybe even more. So big pumps like this don't produce very much head, but they can produce enormous flow rates. And this would be used for moving water from one side of a hurricane barrier to the other, so we don't have much. You don't have much head to work with. You don't have to lift it very far, but you got to be able to move a lot of it fast. There's two general categories of pumps mechanically. One is positive displacement, and the other is rotating or non-positive displacement or centrifugal. The positive displacement pumps, a fixed volume of fluid is displaced or moved every cycle, pretty much regardless of the static head or pressure. These kind of pumps don't produce very much flow rate, but they can produce pretty enormous heads. They're used a lot in the in the oil industry and in similar related industries where the volume that has to be moved isn't or can't be particularly big, but the heads, the energies of the lifts are enormous. The more common pumps in the civil engineering aspect are non-positive displacement or centrifugal pumps. In this case, the volume of the fluid that's moved in each rotation of the pump impeller depends on the static head and pressure in the system. So think of it as the back pressure plays a big role in how much discharge one of these pumps can produce. Examples of positive displacement pumps are screw pumps or Archimedes pumps and reciprocating pumps. And then the ones that don't fall in that category, centrifugal, propeller, and jet pumps are all non-positive displacement pumps. Jet pumps should probably be its own category because a jet pump is actually really a mixed type of pump. A centrifugal propeller pump is used to accelerate a small portion of water to a high velocity, and that's introduced to a larger bit of water, and that jet transfers momentum to the larger bit of water and moves everything along. Nevertheless, whether it's a separate category or not, it has the property that its behavior is extremely dependent on the back pressures in the system. So here's a sketch of a screw pump. In this particular sketch, there's these auger things, or they're called flights. The pump rotates. Let's see, this one looks like it's going to rotate. I have a hard time visualizing this in 3 dimensions. Pretty sure the axis of rotation, or the direction, is going to be that which is indicated by the arrow I just drew. And it's going to grab a chunk of water down here in the flight, and it moves these chunks of water uphill as it rotates, and then these spill off and go on about their merry way. And one of the controlling behaviors of the pump is how deep the water is in this sump side. So they rotate pretty much at constant RPM, and depending on what the depth of the sump is, it determines how much is caught in these flights during each rotation. The photograph on the right is an example looks to me like we're looking down, so the sump is down here and water is being pushed up towards us, and there's actually a gate valve right there to isolate the pump from whatever other hydraulics is in the system. So these can be quite large. They can be bigger around than a tractor trailer truck, and oftentimes they're built on site. The mechanical issues that are important are the bottom bearing, because you kind of want it to not be submerged. So to keep the bottom bearing out of the liquid, the diameters have to be quite large. There's an upper thrust bearing, and there's a motor transmission system. The inertia in these things is huge. So once you get them started running, this is not the kind of thing you turn on and off willy-nilly. You get it moving, pump's moving all nice and steady, all the lubricants working, and then you would open the gate at the bottom and let it start doing its thing. Reciprocating pump, your automotive engine is sort of a reciprocating pump working backwards. Has this volume right here in the cylinder, and as the piston moves up, the volume changes, and so now the volume is much bigger. As it's moving up, water's going that way. It lifts this check valve. It's trying to pull water back this way, but that check valve prevents it from coming back. And when it gets to the top of the stroke, so that total volume right there, when this changes direction, is now pushed down like a syringe. That pushes this check valve back, lifts this check valve, and that volume right there is then sent on down to wherever it's going to. And that's a very basic example of a piston pump, which is a classic example of a positive displacement pump. Some issues on these, if the downstream check valve somehow gets damaged, the pump will destroy itself quite quickly. 1 or 2 strokes and the packing will fail, and then this part of the housing will split, and they leak pretty good. Now these are used a lot in sewage plants still, so when they fail, it's kind of nasty. So a lot of effort is put to be sure that there's a pressure relief on the downstream side so that this check valve can't fail, or at least it has alternate paths. A classic example from your home is this particular piston pump here. This is a 6-speed toilet cleaner, and your toilet bowl performs the role of the cylinder, and then the toilet plunger performs the role of the piston. And you use this when your toilet is clogged with stuffed animals. Yeah, that's it. And that goes ahead and pushes the solids and liquid on downstream so the toilet can perform its role. Positive displacement pumps. They're called positive because as long as nothing breaks, this volume is guaranteed every stroke. Okay, the rotary pumps come in a variety of flavors, and whether they're radial, axial, or mixed more or less depends on the relative direction of water flow to the axis of rotation of the impeller. So in all these 3 diagrams here on the right, this red line I've just drawn is the axis of rotation of the impeller. In this middle one, the entering and exiting water flow more or less go in the same direction as the axis of the impeller. So this would be called an axial flow pump. A radial flow pump, the water comes in the center part and leaves radially at the edge. So these are called radial flow pumps. And then the mixed flow is a little bit of both. Most modern pumps you're likely to encounter are probably mixed flow pumps. And this is only showing a single stage of the impeller. Many of the mixed flow pumps have series of these impellers stacked up several layers thick. And so what's thrown off here is redirected with stator blades inside the pump, which pushes it to the next stage, to the next stage, and to the next stage. So any individual impeller stage can produce whatever head it can produce, but by putting them in series, we can get meaningful amounts of lift out of these. So that's a positive displacement pump, and they're all centrifugal in the sense that stuff is spinning around. A centrifugal pump, the classic one, accelerates water using the impeller. The water enters in something called the suction eye, and it leaves in the discharge eye. And if you're the water looking down the suction eye, what you see is these veins on the impeller, and they're spinning around. As you get close, you realize, oh, this is not going to be comfortable. Those things are going to slap me silly. And so they push you, the water molecule, to the edge of the housing, and then all the other water molecules join you, and you go, getting slapped around kind of hurts, let's get out of here. And that's what leaves in the discharge pipe. Now there's a couple of YouTube videos. Asinine as this sounds, I'm going to go ahead and play them and capture them on this video, and then we'll return in a second.
Centrifugal pumps are the most preferred pumping devices in the hydraulic world. In this video, we will have a conceptual overview of working of centrifugal pumps. At the heart of the system lies the impeller. It has got a series of curved vanes fitted inside shroud plates. The impeller is always immersed in water. When the impeller is made to rotate, it makes the fluid surrounding it also rotate. This imparts centrifugal force to water particles, and the water moves radially out. Since rotational mechanical energy is transferred to the fluid, at discharge sides of impeller, both pressure and kinetic energy of water will rise. At suction side, water is getting displaced, so a negative pressure will be induced at I. Such low pressure helps in sucking fresh water stream into the system again, and this process continues. This is the reason why priming is important for centrifugal pumps. If no water is present initially, the negative pressure developed by rotating air at eye of impeller will be negligibly small to suck fresh stream of water. Impeller is fitted inside a casing, so the water moving out will be collected inside it and will move in the same direction of rotation of impeller to the discharge nozzle. Here you can note one specialty of casing. It has got increasing area along the flow direction. Such increasing area will help in accommodating newly added water stream and will also help in reducing exit flow velocity. Reduction in flow velocity will result in increase in static pressure, which is required to overcome resistance of pumping system. Here you can see more details of vanes inside impeller. They are backward curved vanes with state-of-the-art eye configuration. This vane is extracted from a Kirloskar pump model. If pressure at suction side of impeller goes below vapor pressure of water, a dangerous phenomenon could happen. Water will start to boil, forming vapor bubbles and spoil impeller materials over time. This phenomenon is known as cavitation. More the suction head, lesser should be the pressure at suction side to lift water. This fact puts a limit to maximum suction head a pump can have. Careful pump selection is required to avoid problem of cavitation. Current impeller type is enclosed. Semi-open and open impellers are also in use depending upon application. If the working fluid is cloggy in nature, it is preferred to use open kind of impeller, but they are slightly less efficient. Mechanical design of centrifugal pump is always challenging. A shaft is used to connect between the impeller and motor. Since water pressure inside casing is huge, a proper sealing arrangement is imperative in arresting water leakage through shaft casing clearance. Mechanical seal or stuffing box based mechanism is used for this purpose. Impeller is mounted on bearings, but at suction side of impeller, it is not advisable to fit a bearing since it will block the flow. So bearings have to be fitted at the other end. This means impeller is mounted like a cantilever. For high flow rate pumps, a bearing housing with cooling oil is necessary for improving life of bearings. We thank Kurliskar Brothers for their technical support and creation of this video.
Here we go. Now we'll get to watch the whole video.
Thanks for watching JabscoTech.com. I'm Jeff Lander.
And I'm Mike Irving.
And today we're going to show you how exactly a flexible impeller pump works. Mike?
So we've got these big rubber impellers. This is one of our bigger pumps. And they actually go all the way down to this itty bitty little thing, about that size. All these flexible impeller pumps have something in common. They need a cam. Some cams are in the shape of sleeves. Some are replaceable or removable. And others are actually molded into the pump body. The gist of it is the cam kind of rolls or folds over the vanes and makes a kind of like a larger and smaller cavity, if you can understand.
Mike, why don't we go to the lab and actually show them how an impeller pump works? Let's get out of here.
Let's go. So this is a pretty cool display Jeff and I made. We've got ourselves a commercial duty water puppy, and I took the end cover off. Now you shouldn't run impeller pumps dry, but we put a little bit of lubricant just to make sure it doesn't damage the impeller. It's hooked up to a 500 amp variable power supply, which means we can drop the volts down to about 2.5 volts and still have this spin. Give you an idea what's going on. So that cam is squeezing those vanes. What that does is once the vanes come on this side, it creates a negative pressure, which draws the fluid up into the impeller cavity, down and around, and again, that cam squeezing those vanes, folding them over, pushing the fluid out the discharge. What we're going to do is we're going to put a clear end cover on and give you a better idea what's going on inside the impeller pump. All right, here we go. We've got the clear end cover on. We've got the seal, the O-ring seal around it. We've got some dishwashing liquid here. I'm going to turn the power on. Watch this. That impeller spinning, creating that vacuum. Here comes the material. Swings down, and there it goes. Pumping right through the system. That's pretty cool, huh? It's coming in, going down and around, being squeezed out that side. See if I can slow it down a little bit. How's that? There again. It's coming in, down and around. That cam squeezing those vanes over, pushing the fluid right out. Now check this out. This is the pump running at 2.5 volts. Let me turn it up to 12 volts. That's 12 volts. That pump is running full force. Well, Jeff, that was pretty cool. We used that clear end cover, showed you what's going on inside that pump, the little cavities, how they form, they get bigger and smaller, and how they push the fluid out. I hope that helped out. What do you think?
Yeah, that wraps it up, Mike. Thanks for watching this episode of JabscoTech.com. I'm Jeff Lander.
And I'm Mike Irving.
Come back soon. We'll have some more videos for you.
Okay, so there was two examples of pumps. The first video explains quite a bit the behavior of a centrifugal pump, and the second video, even though it's using a flexible impeller, also captures the spirit of how pumps work. So an axial flow pump is really a ducted fan. It's simply a propeller inside a housing, and the fluid comes in, it's accelerated by the propeller, and it goes out. It's used in high flow, low head applications. The next topic is the suction requirements. Remember, the first video stated that there was a limit to the suction side, and that limit's not something they made up, it's real. And if the suction pressure or the suction lift is suction pressure too small, suction lift too high, we get a phenomenon called cavitation. And cavitation is where the liquid being pumped changes phase, goes from its liquid to its gas state, and then back again really fast. And the back again really fast releases quite a bit of energy. They're little implosions, and they actually will cause pitting, and they'll eventually damage an impeller. And they do it pretty quickly. Not in minutes, but a pump that should run for years, its lifetime can be reduced to months and weeks because of cavitation. So for the piping system with a pump, it's when the absolute pressure at the inflow or at the pump eye falls below the vapor pressure of the liquid, in this case water for this class. In terms of other concepts, that means the liquid has to enter the pump eye under positive pressure. That pressure is called the net positive suction head available. That's what's given to it by the system. And the pump manufacturer provides a value called net positive suction head required. And so the available has to be bigger than the required or the pump won't operate correctly. A centrifugal pump can't lift water unless it's primed. So the second example in the video where they were lifting the green liquid, that was not a centrifugal pump because they were actually able to draw enough suction in the gas phase to lift the green liquid up into the intake tube and on through the system. But with water, which has a lower viscosity than the dishwasher liquid, and a authentic metal-on-metal pump, it's unlikely that they will self-prime. And instead, the first stage impellers have to be located below the static hydraulic grade line in the suction pump at startup. Once the pump is started and running, then the water can be lifted up to almost 30 feet. So in the case where maybe there is that much of a lift, the suction tube has to have an alternate entry point. When you're priming the pump, you literally take a secondary supply of water that's big enough to fill that tube maybe 1 or 2 times over. You put water in the tube as rapidly as feasible at the same time you start the pump, and that will often prime it. Now, if you don't turn the pump on, there's still air will leak back in the system. The water that you fill on the suction side tube will drain out, and it does it pretty fast. So priming a pump is not something you can do willy-nilly. You set everything up, you open the priming valve to release water into the suction tube, and you turn on the pump at the same time. And if all goes well, and sometimes it happens the first time, usually by the second, usually you have to prime them 1 or 2 times, and then the system is good to go. You close all the priming valves and you let the thing run. Then you also, once it's running like that, usually there's a discharge side valve. When you shut the pump down, you're going to slowly close the discharge side valve while the pump is running, and then do the shutdown and complete closing the valve kind of contemporaneously, so that there's no way for air to get back from the discharge side and drain the suction side tube, so you don't have to prime it the second time. Sometimes it doesn't work and you have to prime it again anyway. So the manufacturer supplies a value for the minimum pressure that the pump needs to operate, and that pressure is called the net positive suction head required. So the manufacturer supplies that. For proper pump operation without cavitation, remember the video said that the net positive suction head available, NPSH subscript A, is greater than net positive suction head required, NPSH subscript R. So the R1 is on the manufacturer's information, and the A1 is something that we determine. Depending on the context or literature source, the net positive suction head available is actually just an energy balance. So it's the energy equation rewritten. And it's equal to the absolute pressure of the liquid at the liquid surface in the suction pit, the static elevation of the liquid above the pump inlet eye. So this version of the equation, as I've got it written here, assumes that the pump impeller is below the free surface of the liquid in the suction pit. other literature and other authors do that opposite, and so the sign on this term will change. It should be context sensitive to you. The frictional head loss in the inlet piping, and then the absolute vapor pressure of liquid at the pumping temperature. So this last term we look up on our online toolkit. Frictional loss, static head, this one's certainly a design variable. That is what we determine based on hydraulics, and then the absolute pressure of liquid surface depends on the elevation above sea level and the temperature that the system is going to operate. Here's a simple example. Well, here's an example. 3,000 gallon per minute vertical turbines located 4,000 feet above sea level. Water temperature is 90 degrees Fahrenheit. Suction bill is a 24-inch diameter, reducing to 12-inch at the first impeller stage. And the water level is never less than 8 feet above the first impeller. What's the net positive suction head available under the worst imaginable conditions? Okay, so the first thing that's important is that statement's very handy. And that may not be the case in some analysis you're faced with, but we're told that the impeller is always 8 feet below the water level in the system. Okay, so the steps to determine the net positive suction head available. First, we want to determine the anticipated air pressure at the free surface in the suction pit in feet of water. So we're at 4,000 feet above mean sea level. A reasonable estimate for the change in pressure with elevation at that part of the atmosphere is roughly a half pound per square inch per 1,000 feet of elevation. So at the sea level, we're at 14.7 psi. We go up 1,000 feet, we're at 14.2 psi. We go up another 1,000 feet, we're at 13.7 psi, and so on. We already know that the 1 atmosphere of water is roughly 33.9 feet of water. So we know that by looking it up on the internet. We know that we've lost a half psi per 1,000 feet. We have 4,000 feet, so we're going to lose 2 pounds per square inch. So our air pressure is 12.7 divided by 14.7. That gives us the ratio to multiply that 33.9 to anticipate what the pressure is in feet of water at that 4,000 feet elevation. And then we're going to introduce 85% of that to consider a bad thunderstorm, which typically occurs at about 85% normal atmospheric pressure. So this is a worst case air pressure for the absolute head. I suppose we could get worse than this and put it in a tornado, but if our lift station's in the middle of a tornado, I think we have bigger worries than whether our pump is going to cavitate. So 24.8 feet of head is the absolute pressure head in the system as stated. Next, we want to determine the suction height. In this case, the value was given. We're told the water level is 8 feet or more above the impeller. Next, we want to determine the head loss due to friction in the suction side. The only thing I've included here is the minor loss from the suction bell transition. So kV squared over 2G. We obtain this from the head loss equation based on the nominal pumping rate of 3,000 gallons per minute and the reduced inlet diameter of 1 foot. We look up the minor loss coefficient in a table of loss coefficients for transitions, and the inlet velocity comes out to be around 8.5 feet per second from the discharge value given. That's on a higher side velocity, but not unheard of. So we have 1/10 of a foot of head loss from friction. Then the vapor pressure of water, we look that up in a table of water properties, and we want to find the vapor pressure of water at 90 degrees Fahrenheit, and it turns out that that's 1.6 feet of water, of 1.6 feet of head, expressed as feet of head. So we now have all the values that we need to determine the net positive suction head available. So it's equal to 24.82 plus 8 minus 0.112 minus 1.6 for a total of 31.10 feet. If we use 10% as a margin of safety, we would specify for this system that we want to find a pump that does not require more than 28 feet of net positive suction head for operation. That is, if the net positive suction head at 3,000 gallons per minute for the particular pump is greater than 28 feet, we have set ourselves up for a pumping problem. And either we should use a different pump or modify the suction conditions in the pumping pit. So we have an online tool to calculate those net positive suction heads, because it's actually a reasonably it's an equation not everybody remembers. So here's the net positive suction head equation, and it took an awful long time for the video to load, or for the picture, and it has a drawing, and so it gives us our measurements. So this one says we determine where the pump is, and the distance from the pump center line down to the water surface is this value H sub S. Says static elevation of pump inlet I above liquid. Use a negative value if the water is above the pump. So this equation is almost the same one as before, but there's a sign difference. We want to find the vapor pressure of water at the pumping temperature. That's going to be equal to the absolute. We want to find the absolute head at the liquid surface. That's elevation dependent. And we have the frictional loss terms. Okay, so let's quickly take a look to our problem was at 90 degrees, which we don't have, so we'll go up to 100. And at 100 it says the vapor pressure is 0.949 pounds per square inch. Now we're going to need that in feet of head. So the easiest way in my mind to do it is to convert it into atmospheres and then multiply that result by 33.9. So we have 0.949 divided by 14.75 is 0.06 atmospheres, and there's 33.9 feet of water in an atmosphere times 33.9 for a vapor pressure of 2.18 feet. So I'm going to write that down off screen. And we'll use the other values that were given to us. I believe the frictional loss was 0.12 feet. The flow rate was 3,000 gallons per minute, which we're going to want to convert into cubic feet per second. And the static head, in our case, the water was 8 feet above the pump eye. So we'll return to our online tool. Oh, we don't have the absolute water pressure. Actually, we do. Dr. Cleveland's going to cheat just a wee bit. 24.8 feet of head. Okay, so absolute 24.8. The static is -8, and it's minus if the water is above the pump eye, which is what the problem statement said. Our frictional loss was 0.12, and we're at 100 degrees instead of 90, so our 2.18 feet of vapor pressure. Hit that, and it says we have 30 feet of net positive suction head available. Okay, so the 3,000 gallons per minute, that portion of it is actually important for calculating the frictional loss term. All right, so now you have a tool to calculate net positive suction head available as necessary, so that you can check your work whenever you need to. Okay, last part is selecting pumps. So we need to know about how pumps perform, because we're going to put them into hydraulic systems, and we're trying to match pump performance to the needs of the system. So we usually specify the design conditions, and then we select a pump for the range of applications. A curve of head required by the hydraulic system versus discharge is prepared. That's called the system curve. We'll do one in a second. And then we get a pump curve from the manufacturer and we match the two. Simply, we essentially overlay them on the same axes, and where they intersect is the operating point. That would be the actual working conditions that that pump would function at for that curve. Oftentimes, we want the pump to operate over different ranges. The curves they look curved when we plot them, but they're often reasonably flat for a reasonable range of discharges. And so we can select pumps whose operating conditions can provide the necessary head over a larger range of discharge. I think that'll make sense in a second. So here's a system curve, or a system characteristic curve. So we design our hydraulic system, and for different flow rates that run through the system, there are different head losses. Hello. So the system curve is a plot of the required head versus flow rate in a hydraulic system. We would do that by essentially, we'd write the energy equation for a system and then change the desired flow rate, keep track of the head losses, and that would tell us the amount of head that a pump would have to add to perform as desired. So in this diagram here, let's suppose we have a hydraulic system, and we'll see what this came from in a second. At a discharge value of 0.1, for that, whatever this system is to operate, we need 30 plus units of added head. If we double the flow rate, the required added head goes to 35. If we triple it, we're up over 40. And so the plot of all these together, and they generally curve upward as discharge increases, is called the system curve. Now related to it is the pump curve that the manufacturer supplies, and that tells how much head a pump will generate at different flow rates. They tend to curve downward. And so pump curves look something like that, and where the two intersect is the operating point. So let's consider this system. So we'll look at this first as PowerPoint slides, and then we're actually going to extract these out as an actual hydraulic system. We'll use our online toolkit to construct some performance values of how this system would operate, and that will let us generate a system curve, and then we can go look at some pump curves to satisfy it. So if we analyzed this hydraulic system, we have the total head at position 1 is equal to the total head at position 1 plus any total head here plus added head to the pump is equal to total head here plus any head loss along the way. Okay, that's all the energy equation literally says. The added head of the pump is this H sub P term. The total head at 1 minus the total head at 2, or the total head at 2 minus the total head at 1 is 30, looks like 30 meters in this case. So if there's zero flow in the system as drawn, the pump has to provide at least 30 meters ahead just to keep the water from going the wrong direction. Then as we increase the flow rate beyond zero, we also have to add enough head to overcome the losses in the system. So the losses in the system are this portion right here. And So there's an FL over D term, that's for the pipeline losses. There's an entrance coefficient, a bend coefficient, an exit coefficient, Q squared over A squared over 2G, and perform the indicated arithmetic. And in this particular example, somebody has determined that the added head of the system is 127 times Q squared plus 30. Now see what happens when Q equals 0. Q equals 0, the added head has to be 30 meters just to keep those waters at different elevations. Q anything bigger than 0, let's say 1, assuming this is cubic meters per second, 1 cubic meter per second, we need 127 meters of head plus 30 from the pump, so 157 meters in order to satisfy the needs of this system. So that relationship is just telling us that the added head has to be at least 30 meters just to keep the reservoirs at the two levels shown. If any flows to occur, it has to supply more than 30 meters. Pump curves, these are from the manufacturer. They provide information on discharge head, power input, pump efficiency, speed of the pump, and the net positive suction head. Here's an example of some generic pump curve. Let me get my pen into magenta. So this axis is total dynamic head. On the left side, they're showing it in meters, and the right, doing it in feet, so we don't have to do our own conversions. The horizontal axis, by convention, is usually flow rate. In this case, the bottom's liters per second, and the top is gallons per minute. Each of these curves that I'm highlighting right now corresponds to a different impeller diameter. Generally, the pump housings, or in this case, I'm calling them shaft modules, those don't change. And the way you change performance is you change the size of the impeller until you get one that can't fit inside the housing. Then you got to use a different housing. So this one takes 80 millimeters inlet, 125 millimeters inlet diameter to an 80 millimeter outlet. So it's actually producing a nozzle effect by virtue of that. And then the dash 200 refers to a model number. And so with a 182 millimeter diameter impeller, this is the pump curve that the system will follow, or that the pump will operate on. So for instance, if we're producing 15 liters per second with that pump, that's the 15 liter per second operating point, and we can read across, it will produce about 45 meters of head. We go up to 55 liters per second, so almost 4 times as much flow. The pump only can produce 22 meters of head at that point. That's pretty typical behavior. When we get to 0 liters per second, these points here are called the shutoff heads. And they're the heads that a pump will generate at just slightly above 0 flow rate. Technically 0, but stuff it's in a dynamic equilibrium. So for instance, if we attach this pump to a vertical pipe and turn it on, that pump could hold up 45 meters or so of water in the vertical pipe. If we cut the pipe down to about 25 meters tall, it would have water come spitting out of it at a rate of 55 liters per second. Okay, these curves here, the ones that are labeled percentages, those are wire-to-water efficiencies. So over here in this location, we're not running that pump very efficiently. But we get around here, and these are the efficiency sweet spots. These dashed lines here, those are representing input power in kilowatts for the pump. So for example, to run our 182 millimeter diameter out here at 55 liters per second. We're going to be running just shy of 22 kilowatts of input power. And we'll be operating at about 60% efficiency. So that's not a very efficient use of the pump. This curve down here is the net positive suction head for the 182 millimeter impeller, and so at that point that we're operating at, we're going to need 7 meters. That's an 8 meters of net positive suction heads required. So whatever our flow system is, if we don't have 8 meters of net positive suction head available on the suction side of the pump, it won't perform well. As the impeller diameter gets bigger, the end net positive suction curve, at least for this pump, drops down to that point. So that's a pump curve. Different manufacturers provide their performance data on curves like these. They might look a little different, and you, the engineer, designer, is going to have to search around the curve and find the important points. But they'll be labeled, so you can't look at these willy-nilly. You have to study them a little bit to be sure that you're interpreting the curve correctly. So once we have the information from the manufacturer's curve, we would overlay the pump curve on the system curve and find the operating point. So in this diagram, the operating point is this green circle. In this case, we're comparing two pumps, Pump A and Pump B. Pump A, for this particular system curve, can't produce enough head at any flow rate, so it's not a good choice at all. Pump B has its matching point right there, so that's where it wants to operate. But this area all in here, that pump could be used. It generates more head than is necessary. And so we would, in some sense, be wasting energy. But the point is Pump B can operate anywhere along that system curve and provide enough head. What to do with the excess head is a different issue. Here's another diagram conveying the same information. So here's a pump curve, here's a system curve. The operating point is right there, so this one works at 9 cubic meters per hour at 58 meters of head. The net positive suction head is around 4 meters. That's what's required. And anywhere on this side, shaded area, that pump will operate. I mean, we could pump water with it, but its efficiency isn't very good. In this case, the sweet spot of efficiency is right about there. So we're pretty close to a most efficient operating point in this particular example. We can use multiple pumps if we can't find a single pump that performs as desired. If we put pumps in parallel, they'll add flow for a given head. If we put them in series, they add head for a given flow rate. So here's an example of two pump A's and one pump B. The two pump A's are in series. The pump B is in parallel to the two pumps A. And so the composite pump curve is this guy. And so if this is our system curve, we now can operate all the way out to that point. So there's one pump A, there's two pump A's in series, and there's a pump B. And when we composited them, we did the parallels were adding flow for a given pump rate. Here's another diagram. It's depicting the same thing. So these are 1, 2, 3 pumps in parallel, and here's 1, 2, 3 pumps in series. And even though we show these as almost perfect additions, in real systems they're not perfect. 2 pumps in series doesn't quite produce twice the head of one pump. Plus the pumps have to be matched and somewhat identical because they can be selected so as they fight each other. But for design purposes, this addition is pretty close to correct. It's close enough to be able to make reasonable designs and select pumps for a pumping system. Hello and welcome to a supplemental video. I want to go through some more on system curves, and I actually want to use this example, and we're going to work through the example as written. We'll develop a system curve, and then I want to use an online tool making a series of changes to a fabricated pump curve to demonstrate that you can extract the same behavior using an online tool. So I'm copying the drawing right here onto a piece of paper, and then we'll go to the piece of paper. So we have pool elevation to 200 meters on the left, 230 meters on the right. We have a pump here. We have a pipeline that's 1,000 meters long, 40 centimeters in diameter. We're told the friction factor is 0.015. And if I go up on the internet and look up the entrance, bend, and exit coefficients, for the entrance I get a coefficient of 0.5. For the exit coefficient on the right, I get 1.0 exiting in the bottom of that reservoir. And for this bend right here, I chose 0.3. And I got those simply by going to the internet. We can look at it. Pretty sure it should be here in minor loss coefficients, and basically I was picking through information like that, and I could conceivably actually validate it. So there's my drawing refabricated, and this is mostly for my own use for doing this online, so I'm not going to worry about getting it blown up big enough per se. Okay, that's the one I want to work at. Okay, let's first work through this the long drawn out way. So we have reservoir 1 and 2, and if we apply the energy equation, we have total head at 1 plus the added head at the pump is equal to the total head at 2 plus the head losses. So the added head the pump has to produce is H2 minus H1 plus head loss. Let's expand out. Well, we can do H2 minus H1 right away. That's 230 minus 200 is 30 plus the head loss term. Let's make a quick change that v squared over 2g is equal to 1 over 2g times q squared over a squared, which equals 1 over 2g times q squared. Now, a squared is pi d squared over 4, so we would go pi squared d to the 4th, and 4 squared is 16. And so this becomes equal to 8q squared over pi squared g d to the 4th power. And this is the form that we'll use in the head loss equation. So let's now expand the head loss equation out. There's F L over D plus the entrance loss plus the bend loss plus the exit loss, and that's all multiplied by 8q squared over pi squared g d to the 4th power. Let's go ahead and substitute numerical values. So this is plus. We're told the friction factor is 0.015. Pipe length is 1,000. Diameter here is 0.4. Plus the exit is 0.5 plus bend, 0.3 plus 1.0, all times 8 q squared over pi squared g and 0.4 to the 4th power. Q is going to remain unknown. We have a 30 here, and that's our required head that we have to add to make the system operate at a desired flow rate. If the flow rate is 0, all we do is have to magically add 30 meters ahead. Let's go ahead and evaluate the contents of the square brackets. So 0.015 times 1,000 divide by 0.4, that equals, do that again, 1,000 times 0.015 divided by 0.4. So this is 37.5 plus 0.5 plus 0.3 plus 1.0 plus 0.5 plus 0.3 plus 1 equals 39.3 times 8 times q squared pi squared g 0.4 to the 4th power. Go ahead and try to express the remaining constants. So 39.3 times 8 is 314.4. 314.4 q squared over pi squared, g is 9.8, 0.4 to the 4th power. I'm going to go ahead and save, let's see, store that into the storage register. Now I'm going to divide by pi, divide by 9.8, divide by 0.4 once, divide by 0.4 twice, divide by 0.4 thrice, divide by 0.4 4 times, and so this equals 30 plus 126.9 q squared. So that's my required pump head. 30, 126.9. And that was for a friction factor of 0.015. That will make sense shortly. Okay, well, let's go ahead and pick a few values of Q in the computed H sub P. So I want to pick values. Let's see, Q is 0. I'm making these up. 0.13, 0.23, 0.35, 0.44, 0.51, 0.58, and 0.64. Now I chose those not entirely arbitrarily. Those are ones I think I can achieve by a different technique using an online calculator. So we'll see how close we can come to that. Okay, so we take the Q and we square it. We multiply that by 126.9. We add to that 30, and so we get 32.14. 0.23 squared times 0.23 squared times 126.9 plus 30 equals 36.71. 0.35 squared times 126.9 plus 30 equals 45.54. 0.44 squared times 126.9 plus 30 equals 54.56. 0.51 squared times 126.9 plus 30 equals 63.0 some other numbers, but close enough. That 0.58 x squared times 126.9 plus 30 equals 72.68. And last one, 0.64 times 126.9 plus 30 equals 111.2. I think I made a mistake. Let's try that again. 0.64 squared times 126.9 plus 30. Yeah, I did something goofy. This is 81.9. Okay, so that was doing it by hand, and this all has a constant friction factor. But let's say we're lazy, like I am, and we have this cool online tool. How can we trick this into doing our bidding for us? Well, we know the left pool elevation is 200 meters. The inlet loss coefficient was 0.3. The pool elevation on the right was 230 meters. The exit loss was 1.0. Pipeline length was 1,000 meters. The fitting loss was this was 0.5. The fitting loss is 0.3. And there's no second fitting, so we'll leave that. We'll disappear that. Pipeline diameter is 0.4. 0.00003 will be my initial guess at sand roughness height. Kinematic viscosity 1e minus 6 should be correct for SI units. Gravitational acceleration is 9.8 meters per second squared. And now let's look at arbitrary shutoff heads, 90, 80, 70, and 1 and 2. So we're going to let it fit this pump that doesn't exist, and it says at 70, at a discharge of 0.72, we produced 85.3 meters of head. So that's the online. And what I'm now going to do is systematically reduce the pump performance. So we'll make that an 80, 70, 60. And now for 0.65, I got 75 meters of added head. But if I look at my friction factor, I'm quite a bit lower than we did in the original problem. So we'll go back, bring this back to its original values, 90, 80, 70, and see, friction factor's too low, so I want my roughness to be bigger. Try that. Roughness 0.012, still too small. Pipeline friction factor too big. Still a little too big. How about 15? Okay, that's as close as I'm going to get to 0.015, I think. I'll make one more. Good enough. Okay, so we'll make all of our decisions on that. So we return to that. We now have discharge of 0.65, an added head of 85. Now I'm writing these down on the other sheet of paper. When we go back to it, we can see how close we get with the by hand versus online. Okay, bear in mind the online, all we have to do is interpret the picture and systematically run through some input values. We don't have to think as hard. 80, 70, 60. Okay, so 0.59 is 76. We have a 0.58, so we're going to use that, call that good enough. 70, 60, 50. 0.52 is 66. We have a 0.51, so we'll live with that. 60, 50, and 40. We're at 0.44. Notice our friction factor is hovering around 0.015, which is what we're after. 0.449 is 56.75. We're at 0.35, which is 47. Friction factor is 0.016-ish. And discharge at 0.23, I got 37.43. Now it's going to take a little trickiness as we're getting close to shut off here at 35, 30, 25, changing the pump curve a bit because I want to try to get, ooh, pretty close. At 0.116 is 33. Let's see if I can slightly reduce that. Ooh, I like that. So 0.013 and I get 32.50. Okay, let's go back to the overhead and look at the results. Okay, these are flow rates. This column is the added head produced using that equation. This column is the added head produced by using our online calculator. The added head by hand, added head online, essentially the same number. Very close, very close, very close, pretty close, and pretty close, and again pretty close. Remember, this one had a constant friction factor, and this one had a friction factor that was 0.0156. It varied, but it hovered around there, and it correctly reflected that as the flow rates change, the friction factor changes slightly. They're not constants. The point being, all we had to specify for this was the geometric information, what the fluid was, and then by faking a series of pump curves, we're able to get the added head required by the system. So if we were to plot that, let's see, 30, our plot looks like that. Then when we go to an actual pump, we would intersect it and we get that point. So let's suppose we have an actual pump that has shut off of 56.2 meters, and at 1, 2 is 38 point, oh, it's not that bad, 41.2 and 38.7. So let's say that's the pump that we get from a manufacturer. We go back to our online tool. We have everything else already entered. And so now we enter shutoff head 56.2. Our operating head 41.2 at a discharge rate of 1 and 38.7 at a discharge rate of 2. Run it, and it says that that system will operate with a total head of about 50 feet, and the discharge is at 39, almost 40 meters cubed per second. So our system for this pump that I just created operates in this range. Our system for this pump I just created operates in that range. That's how to use online tool to generate system curves if you have to in a hurry. It seems like more work, but this could be done on a phone, whereas I dare say doing it by hand, you need a piece of paper to figure it out. Okay, that concludes this video. Thanks for your attention.